Okay, today we're going to talk about transforming exponential functions. And exponential functions and their transformations look similar to the transformations we did on absolute values. So when we had a graph like 2, value of x minus 3 plus 4, maybe I should write a 4, not a d. We looked at this and we went, well, it shifts it to the left 3. Nope, sorry, to the right 3. Mixing up my left and right. Gonna go in the positive direction 3. Absolute value is a v. So I'm gonna go in the positive direction 3 and up 4. Okay, we call this 3 our horizontal shift. We call our 4 our vertical shift. The 2 was known as our vertical stretch. If it's a number larger than 1, we called it a stretch, or if it has an absolute value larger than 1, or we called it a stretch if it was less than 1, we called it a compression, because it's going to kind of shrink it down. We talked about it in terms of slope on the absolute value, because that was a term you're very familiar with. Remember, if it was negative, we made it go down. So we said that was a reflection. You always do these reflections before you do the translation part. So I'd reflect over the x-axis first. So I'd make my v open down, then I'd translate it. So vertical stretch, potentially compression, or also sometimes called a vertical dilation. And we did do some of these in function form. And that general function form was, we said f of x was absolute value of x, and g of x then was some value a of f of x minus c plus d. And that minus c part, this f a little neater, was my horizontal translation, my plus d was my vertical shift, and my a was my dilation. They're going to introduce a b here, and b is simply going to be a horizontal stretcher compression, and we're going to change that. We'll talk about that at a later date. But if it shows up as b, that's what it means. You can just, they're going to use that to change it b that I'm going to talk about in just a second here. We're going to apply this to exponential functions. So I'm going to jump to a new page here. And we're going to start with our basic exponential function, y equals ab to the x. A, again, being my vertical stretch or compression, dilation. If there's no plus c or d, it's my y-intercept, or my initial value. A lot of times we can get away without needing a plus c or d, so it can just be our y-intercept. B, known as our growth or decay factor. And it is often decay, sometimes called constant multiplier, or if you remember geometric sequences from last year, it was the common ratio. Multiplier. There we go. Having trouble spelling this morning. So what does doing something like changing the b value do? Okay. Well, changing the b value is going to change how steep it is. So if I've got 2 to the x here, and I'm just going to do this in table form. So x is, say, 0, 1, 2, 3. 2 to the 0 is 1. 2 to the first is 2. 2 to the power of 2, so that's like 2 squared. That's 4. 2 to the third here is going to be 8. Now we're going to repeat with 5. 5 to the 0 is still 1. 5 to the first is 5. 5 to the second is 25. And 5 to the third is 125. That one's growing a whole lot steeper. This is going to be 8. So here, my basic exponential curve looks like this. That's my 2 to the x. I'm going to do my 5 to the x here in blue. $25 is going to be somewhere way up here. I can assume that that's a better curve than I'm able to draw right now. You could say that's either a vertical stretch. We call it a horizontal compression because there isn't a perfect scale factor for what I'm multiplying by to stretch it out vertically. Okay. And it can show up as lots of different options. Okay. So AB to the x. This is going to be me working out the worked example from page M3 122 in the book, kind of explaining that. So they're doing the transformation with the b here inside. So this is a capital B, not the little b, and y equals AB to the x. So how does that translate? That translates as y equals AB to the capital BX, because the inside must go where the x is. So my example here is we're going to go ahead and show that 1.10 to the 1/12th power to the bx is simply equal to 1.10 to the x. Okay? So I know from my exponent rules, which we reviewed a little bit ago in the video from Monday, that I simply multiply my exponents. So that makes this 1/12 times bx, or bx over 12. And if I want to solve for b, since my two bases are 1.1 and they are equal, my exponents must be equal. To isolate b, I'm going to multiply both sides by 12. So bx equals 12x. Now, I can't exactly divide by x without eliminating answers, because 0 would keep it true. But if x is not 0, which I guess it could be, but for non-zero values of x, b then has to be 12. So it's always dangerous to just do this like divide by x, because it eliminates some answers like 0. Oops. But in this case, it does work out for all non-zero ones, b has to be 12, and that's what we're trying to get at. So this b factor is just really going to adjust this b. It's just going to change that b by using exponent rules.